Ever hit that moment? Your code, the code you've poured hours into just
Yeah.
freezes.
Yeah.
Or it starts chugging along like a rusty old engine, slowly gobbling up every last byte of memory until, bam, it crashes. Out of memory error.
Been there. It's painful.
And you're sitting there, you feel like a wizard with algorithms, but suddenly memory usage feels like this total black box, a mysterious force completely beyond your control.
Right.
You're left wondering, is there some invisible custodian cleaning up? Or am I just doomed to wrestle with these memory ghosts forever?
Memory ghosts. I like that.
Well, today we're pulling back the curtain on one of computing's real unsung heroes.
Yes.
Garbage collection.
GC. We've sifted through quite a stack of sources, really, from historical deep dives to some pretty cutting-edge research, all to give you, our curious programmer listener, a kind of shortcut to understanding this critical yet often unseen manager of your digital workspace.
It's so true. Modern programming languages, and honestly, thank goodness for them, they abstract away so much of the nitty-gritty of memory management. Huge productivity boost.
Totally. But really understanding how garbage collection, or GC, actually works under the hood, it's incredibly empowering.
How so?
It helps you diagnose those baffling performance issues, write more efficient code, and really grasp why your applications sometimes seem to, have a mind of their own when it comes to memory.
That's the perfect way to put it. We've all been there, right? Chasing down a bug that only pops up after hours, or seeing an app inexplicably slow to a crawl.
Yep.
But before we get into the solutions, let's really set the stage. Why do we even need garbage collection? What was it like before this invisible custodian showed up?
Oh, it was, frankly, a programmer's nightmare. Before GC, memory management was entirely manual. Every single piece of memory you allocated.
You had to clean up yourself.
You had to explicitly deallocate it when you were done. Think of it like living in a house where you have to label every single item, put a sticky note on it, for disposal once you're finished.
Okay, T.
And if you forget one thing, it just piles up. Make a mistake, try to dispose of something still in use, or worse, dispose of it twice.
Yeah.
You got real trouble. This led to some truly insidious bugs.
So we're talking about more than just a messy digital house here. What were the really dangerous pitfalls, the things that kept developers up at night?
The list was long and, painful. One of the most common was dangling pointers.
Okay, what's that?
Imagine you free a block of memory, right? But your program still holds a pointer, an address, to that now invalid location. If it then tries to use that pointer, it's essentially trying to access memory that might have been reused for something completely different. Leads to unpredictable behavior, security holes, or just outright crashes.
Nasty.
Another one, double free bugs. Accidentally trying to free the same memory block twice. That can corrupt the memory manager's internal bookkeeping, makes your whole system unstable.
Yikes.
But maybe the most frustrating problem was memory leaks.
The classic leak.
Simply failing to release memory you don't need anymore. Over time, these little oversights, they just accumulate, slowly but surely exhausting your application's available memory until it just grinds to a halt or crashes.
Like that colleague who never clears her browser tabs.
Exactly. Eventually, the whole system just collapses.
Yeah.
These issues, they dramatically increased code complexity and made debugging an absolute nightmare.
Wow. So the stakes were incredibly high, like finding a needle in a haystack made of bytes with the entire system on the line. It sounds chaotic, error-prone.
Totally chaotic. And that landscape persisted until around 1959. That's when American computer scientist John McCarthy, who was also a co-founder of AI.
The Lisp guy.
He introduced the concept of garbage collection for Lisp. It wasn't just an improvement. It was a fundamental paradigm shift.
So McCarthy didn't just solve a technical problem. He kind of laid the groundwork for the sort of high-level programming we take for granted now. How did GC fundamentally change the game?
It automated all that drudgery. Garbage collection is all about automatically reclaiming memory from objects that are, and this is key, no longer referenced by the program.
Finding a trash.
In essence, yeah. It identifies and disposes of the garbage that's accumulated in memory. This fundamentally simplified programming. It freed developers from that error-prone task of manual memory bookkeeping.
So they could focus on the actual logic.
Exactly. Focus on the application logic, which, paved the way for far more robust and complex software.
It really sounds like a foundational shift and enabled whole new kinds of applications. No wonder that today languages like Java, C#, Go, Python, they all rely heavily on some form of automatic memory management.
Absolutely. And at its core, this whole process relies on two fundamental principles, the heap and reachability.
Okay, the heap.
The heap is basically where most of your dynamically allocated objects live. Your strings, your arrays, instances of classes you define. It's this large shared pool of memory. Different from the stack, where local variables and function calls live. Think of it as the main storage room for all the dynamic data your program creates and uses.
Got it. Storage room. And reachability.
Reachability.
Yeah.
That's the central idea for finding the garbage. An object is considered live or reachable if your program can still somehow access it.
How does it know?
Well, this access starts from what we call the program's roots. These are like the anchor points. The global variables, local variables on the call stack of functions that are currently running, maybe even CPU registers.
Okay.
The garbage collector kind of visualizes your program's objects and how they connect as an object graph. It then walks this graph, starting from those roots. Anything it can't reach by following these connections.
That's garbage.
That's garbage.
So if I have code like, say, user name, Alice, that user variable is a root, right? And the object is reachable. But then if I do user equal null, what happens?
Exactly. Now the object name, Alice, is no longer reachable from that root. The link is broken. The GC will eventually spot this, and its memory becomes eligible for reclamation.
Okay.
And this idea extends even to complex stuff, like an unreachable island, where, say, object A points to B, and B points back to A, but nothing outside that little loop points to either A or B.
So even though they point to each other...
If the whole group isn't reachable from a root, the whole island is garbage. It's important to remember, though, GC collects what it can prove is unreachable, not necessarily what will never be used again.
A subtle distinction.
Yeah, proving future non-use is basically impossible, like the halting problem in computer science. So GC designers have to err on the side of safety. Better to keep something potentially unused than free something still needed.
Okay, so we get the why avoiding chaos and the basic principles. Heap, roots, reachability. But how does this invisible custodian actually do its job? It's not just one magic algorithm, is it?
Oh, far from it. There's no single best solution. Different languages, different runtimes, they employ a whole variety of sophisticated strategies, often combining them. Actually, before we dive into the collection algorithms themselves, it's worth a quick mention of how memory typically gets allocated in the first place.
Right.
Two common ways are bump the pointer allocation, super fast, just move a pointer forward in a big chunk of free memory. Simple.
Okay.
And then there's free list allocation. This keeps track of available memory blocks using lists. More flexible maybe, but can sometimes lead to fragmentation, little gaps everywhere.
Right, fragmentation. We'll come back to that. So allocation happens, objects live, then die. Let's peel back the layers on these classic GC algorithms. They're the building blocks, you said.
Absolutely. The foundations. Let's start with reference counting. This one's pretty intuitive.
How does it work?
Each object basically keeps a counter. How many other objects or roofs are pointing to it?
Okay, a popularity count.
Sort of. This count goes up when a new reference is made, down when a reference is removed. When an object's count hits 0,
It's gone.
it's immediately deallocated. The big advantage here is prompt reclamation. Memory is freed up pretty much instantly. It's also relatively simple to implement.
Sounds almost perfect, but I'm guessing there's a catch.
There is a big one. It cannot collect cyclic data structures.
Ah, the island problem again.
Exactly. A points to B, B points back to A. If nothing else points to them, their counts will stay at 1 forever, even if they're totally unreachable from any root.
So they leak memory.
They leak. Plus, constantly incrementing and decrementing those counts, especially in multi-threaded programs, can add, significant performance overhead. Python's main implementation, CPython, uses reference counting, but it needs a helper GC just to deal with those cycles.
Okay, so reference counting is simple, fast for non-cycles, but has that cycle blind spot. What's next?
Next up, we have mark and sweep. This is a different approach, a tracing collector. It works in 2 phases.
Mark and sweep. Makes sense.
Phase 1, mark. The collector starts from all the program's roots, walks the entire object graph, and marks every single object it can reach as being alive.
Okay. Tags the survivors.
Pretty much. Once marking is done, phase 2, sweep. The collector then scans the entire heap linearly. Any object it finds that wasn't marked.
That's the garbage.
That's the garbage. Its memory gets reclaimed, usually added back to a free list for future allocations.
So it sweeps up anything not marked alive. Does this solve the cycle problem?
It does. Because if that ABA island isn't reachable from a root, neither A nor B will get marked. So the sweep phase cleans them up. Major win over basic reference counting.
Okay, sounds better. Downside.
Traditionally, the big one is stop the world. STW pauses.
Stop the world. Sounds dramatic.
It is. Your entire application literally halts, freezes completely, while the marking and sweeping happen. For interactive apps like a game or a UI, that can feel like a really annoying stutter or freeze.
Not ideal.
Not ideal. And it also tends to lead to that memory fragmentation problem we mentioned. The heap ends up with lots of small scattered holes of free memory. Even if you have enough total free space, you might not be able to allocate a large new object because there isn't one single contiguous block big enough.
Okay, so mark and sweep handles cycles but causes pauses and fragmentation. What else is in the toolbox?
This brings us to copying collectors, sometimes called semi-space collectors. These tackle fragmentation head-on.
How?
They divide the heap into two equal halves, two semi-spaces. Let's call them from space and to space.
Okay, 2 rooms.
Right. When GC runs, it finds all the live objects in the currently active from space. Then it copies them one by one over into the to space, packing them tightly together as it goes.
Ah, so it compacts them automatically.
Exactly. And all the pointers to those objects get updated to their new locations in the to space. Once all live objects are copied, the roles of the spaces swap. The old from space is now totally empty, ready for new allocations, and the to space becomes the new from space.
That's clever. Cleans up and defrags in one go.
Huge advantages.
Mm-hmm.
Automatic compaction eliminates fragmentation completely, and fast allocation, because you can use that simple bump the pointer method in the nice empty new space.
Nice.
Plus, the work it does is proportional only to the amount of live data. If most objects are garbage, which is common for short-lived stuff, it's super efficient.
Okay, again, sounds great. The catch.
High memory overhead. You essentially need double the memory you're actually using at any time, because only half the heap is active.
Ouch. Twice the memory footprint.
Yep, so these are often used for specific parts of the heap, like young generations, where objects are expected to die very quickly anyway.
Okay, so copying trades memory for speed and no fragmentation. One more classic.
One more classic, mark compact collectors. These try to get the best of both mark and sweep and copying.
The hybrid approach.
Sort of. It starts with the mark phase, just like mark and sweep, identifying all the reachable objects. Then the compact phase. Instead of just sweeping up the garbage, it relocates all the live marked objects. It shifts them all down to one end of the heap, squishing them together. This consolidates all the free space into one big continuous block at the other end. And crucially, like copying, it updates all the pointers to the moved objects.
So it gets the cycle handling from mark and sweep and the compaction, like copying, but without needing double the memory.
Precisely. Handles cycles, compacts memory, reduces fragmentation, and has less memory overhead than a pure copying collector.
Seems like the winner.
Well, the trade-off is complexity. That compaction phase, figuring out where everything goes and updating all the pointers, can be quite complex and computationally expensive. And like mark and sweep, it typically still involves stop-the-world pauses, though may be structured differently. Mark compact is often used for those older generations in systems like Java's JVM or .NET CLR, where objects tend to live longer, and preventing fragmentation over the long term is really important.
Okay, wow. Reference counting, mark sweep, copying, mark compact, those are the fundamental building blocks. But you said modern systems often combine these. The real world rarely settles for just one simple solution, does it? How have engineers taken these fundamentals and built the incredibly sophisticated adaptive systems we see today? This is where it gets really interesting, I bet.
It absolutely does. Modern GC is fascinating.
Yeah.
One of the most impactful optimizations building directly on those classics is generational garbage collection.
Generational, like based on age.
Exactly. It's built on a very strong empirical observation called the generational hypothesis. Most objects die young.
Huh, like digital infant mortality.
Pretty much. So to exploit this, the heap is divided into different generations. Typically, a young generation, or nursery, and an old generation, or tenured space.
Okay.
New objects are always allocated in the young generation, and because most die young, this area is collected very frequently, often using a fast copying collector. We call these frequent young gen collections minor GC.
Makes sense. Collect where the action is.
Right. Objects that survive a few of these minor GCs, proving they're longer lived, get promoted or tenured, they move to the old generation.
And that gets collected.
Much less frequently.
Yeah.
Because objects there have already shown some staying power. When the old generation is collected, often along with the young, that's called a major GC or full GC, and it typically uses a slower but more space-efficient algorithm like Mark Compact to deal with fragmentation over the long haul.
That's really clever. Focus the effort where most garbage is created. Better throughput, shorter average pauses. But wait, what if an object in the old generation suddenly points to something brand new back in the young generation? How does a minor GC know to keep that young object alive? Does it have to scan the entire old generation every time?
Great question. That's a key challenge, the old to young pointer problem. Scanning the whole old gen during a minor GC would defeat the purpose. So they use clever tricks. Common ones are card marking or remembered sets. Imagine the old generation's memory is divided into small chunks, like index cards. Whenever the application code modifies an object on an old card so that it now points to an object in the young generation, that specific card gets marked as dirty.
Ah, like a flag.
Exactly. So when the minor GC runs, it only needs to scan the roots plus any objects on those few dirty cards in the old generation. It doesn't need to scan the entire old gen. It drastically reduces the work for minor GCs.
Very efficient. Okay, so generational GC is huge. What else is in the modern toolkit? You mentioned pauses.
Right, those dreaded stop-the-world pauses. Another huge area of innovation is incremental and concurrent collection. The main goal here is to reduce or even eliminate those long application freezes.
How?
Incremental GC breaks the GC work, like marking or sweeping, into smaller chunks. It does a little bit of work and lets the application run for a bit, then does a bit more GC work, interleaving them.
Like sweeping the house room by room instead of all at once.
Good analogy. Yeah. It reduces the length of any single pause, even if the total GC time might be slightly longer overall.
And concurrent GC takes that even further.
Much further. Concurrent GC allows the GC threads to run at the same time as your application threads for most of the collection cycle. The application doesn't, or barely, stops.
Whoa! How does that even work? Isn't the application changing things while the GC is trying to figure out what's garbage? The moving target problem?
Exactly. It's incredibly complex.
Yeah.
To handle this, concurrent collectors rely heavily on techniques like write barriers.
Barriers.
Think of a write barrier as a tiny bit of code that the compiler inserts. Whenever your application code is about to modify a pointer like obj field, some other object, this barrier code runs first. It usually notifies the GC about the change, perhaps by recording the old value or marking an object needing rescan.
So the GC stays in sync.
It helps the GC maintain a consistent view of the object graph even while the application is messing with it. Abstractly, people often talk about tricolor marking, white, gray, black objects, as a way to visualize how these concurrent collectors keep track of progress safely.
Fascinating. So concurrent aims for minimal pauses. What about just making the pauses shorter?
That's where parallel garbage collection comes in. This leverages modern multi-core processors. Instead of one GC thread doing all the work during a pause.
Use multiple threads.
Right. Multiple CPU cores work together in parallel to perform the GC tasks, like marking or copying during a stop-the-world pause.
So it still stops the world.
Yes, that's the key distinction from concurrent GC. It's still STW. But by throwing more CPU power at the problem simultaneously, it dramatically shortens the duration of that pause. This is great for improving overall application throughput, especially on servers with lots of cores.
Okay, generational, incremental, concurrent, parallel. We've just navigated a whole labyrinth of strategies. For a programmer listening, the natural thought is, okay, great theory, but what does this mean for my code day to day? How do I know which of these my language is using? Or can I even choose?
That's the million-dollar question, right?
Okay.
And it often boils down to a fundamental trade-off, throughput versus latency.
Throughput versus latency. Explain that.
Okay, throughput is basically how much useful work your application gets done over time. High throughput means less time spent in GC pauses, more time running your actual code. A high throughput GC might allow for longer, but less frequent, pauses. Think batch processing, data analytics jobs where overall completion time matters most.
Got it. Just get it done fast overall.
Exactly. Latency, on the other hand, is about responsiveness. How quickly does your application react to an event? A mouse click? A web request? Low latency GCs aim for the shortest possible pauses, ideally sub-millisecond.
Who needs low latency?
Interactive UIs, games, high-frequency trading systems, web servers serving user requests. Anything where a noticeable pause is bad news.
And those stop-the-world pauses directly hit latency.
Directly. Even brief freezes can be awful for these systems. It leads to what's called the tail latency problem. Maybe the average pause is okay, but those occasional unpredictable long pauses really hurt user experience or system stability.
Right. And there are other costs too, right? Like memory use.
Definitely. There's memory overhead. The GC itself needs memory for its own data structures. Copying collectors need that extra semi-space. Sometimes you make the heap larger just to make GC run less often, trading space for time. And there's CPU overhead too, the time the processor spends running GC code instead of your code.
And fragmentation is still a concern.
Always lurking, especially for non-compacting collectors. It can lead to those frustrating premature out-of-memory errors even when there seems to be enough free space overall. That's why compaction, either via copying or more compact, is so valuable, especially for long-running apps.
This throughput versus latency dilemma, it feels like you can't optimize for everything at once. You have to pick your poison, almost.
It's very much a balancing act. Different language runtimes make different choices, often giving you options.
So how do some popular platforms handle this, like Java?
The Java Virtual Machine, JVM, is famous for offering a lot of choice. You can really tune it. For years, collectors like CMS, Concurrent Mark Sweep, and Parallel GC were common. Now, G1, garbage first, is often the default. Yeah, it's server style, aims for more predictable pause times. It divides the heap into many small regions and tries to collect the regions with the most garbage first, hence the name. It's a good balance.
But Java also has those cutting edge ones, right?
Oh yeah. For ultra low latency, there's ZGC, Z garbage collector, and Shenandoah. These are amazing feats of engineering.
ZGC, what's special there?
ZGC is designed for massive heaps, terabytes even, with the goal of keeping pause times consistently under a millisecond, regardless of heap size. It's fully concurrent for almost all its work, using advanced tricks like colored pointers embedding GC info directly into memory addresses and load barriers, which check pointers when they're read, not just written. It's NUMA aware too for modern multi-socket servers. Shenandoah is similar, another fantastic low-pause concurrent collector. These let Java run really demanding, latency-sensitive stuff.
Wow. Okay, what about .NET?
.NET CLR also uses a generational approach, Gen 0, 1, 2, plus a large object heap, but it offers distinct GC modes. There's Workstation GC, which runs concurrently and is tuned for responsiveness, like for desktop apps. Then there's Server GC, which uses parallel threads during STW pauses for maximum throughput on server workloads. So you choose based on the application type.
Makes sense. Client versus server. And Go. Golang's known for concurrency.
Exactly. Golang's GC is tightly integrated with Go routines. It uses a concurrent mark sweep strategy, really prioritizing low latency. Most of the work happens alongside your application code.
Does it compact?
Interestingly, no. Go's GC is non-moving. It doesn't relocate objects. This simplifies the GC and avoids pointer updates, which helps with concurrency. The downside is potential fragmentation, but Go's allocator is quite sophisticated and works hard to mitigate that. Developers can tune it with environment variables like GeoGC and Goldman limit to influence the time-space trade-off.
Fascinating. And Python. We mentioned reference counting.
Right, CPython uses that hybrid approach. Reference counting is the primary mechanism, quick prompt deallocation for most objects. But because of the cycle problem,
it needs the backup plan.
It has a supplemental generational cycle collector. This runs periodically, specifically to find and break those reference cycles that reference counting alone would miss.
What really stands out here is, well, there's no silver bullet, is there? No single best garbage collector. It's really all about matching the tool to the job your application's specific needs. High throughput engine, responsive UI, giant heap, different answers.
Absolutely. Garbage collection truly is an unsung hero. It didn't just make programming easier, it fundamentally made it safer, wiping out whole classes of bugs like memory leaks and dangling pointers. It enabled the kind of complex software we rely on totally today. From McCarthy's original insight in Lisp to these incredibly sophisticated, adaptive, concurrent generational systems in modern JVMs, .NET, Go, Python. It's just this field of constant, amazing evolution.
And understanding these crucial trade-offs we talked about, throughput versus latency, memory overhead, fragmentation, it isn't just academic, right? It really empowers you as a programmer to write better, more memory-efficient code, sure, but also to make smarter decisions when you're tuning your runtime or maybe even choosing a language or framework for a new project.
Exactly. And the journey isn't over. Researchers are constantly pushing boundaries, thinking about UMA-aware GCs that understand modern hardware topology, how to manage new kinds of persistent memory, creating even more specialized collectors for specific niches, like maybe request private GCs for web servers. The quest for that pauseless, ultra-efficient GC, it's unending because software needs and hardware capabilities are always changing.
So thinking about that constant evolution, if GC is this invisible, ever-adapting custodian, always trying to be smarter, faster, less intrusive, What do you listening think the next big breakthrough might be? What's the next frontier for automatic memory management? And maybe how will new hardware like persistent memory systems fundamentally change what garbage even means? What memory challenges are you grappling with in your own projects right now? We'd genuinely love to hear your thoughts on these questions. Drop us a comment below. Let us know what you think. Thanks so much for joining us on this exploration into the hidden world of garbage collection. That's about it for this deep dive. We really hope you feel a little more well-informed, maybe less mystified about those unseen forces managing memory in your code.
Understanding these fundamentals really does empower you. Keep learning, keep exploring those internals, and keep building amazing things.
Until next time, keep diving deep.